Hello students, welcome to online chemistry classes. This is 5th class in some basic concepts of chemistry. In the last class we have seen how to convert one unit into another unit. We have to arrange it properly and do some simple mathematical steps, and we get one unit converted to another unit. I have also given 3 questions as homework. I hope that, as always, you have done your homework very sincerely, and you might opt in right answers also. But just to verify your answers, with these answers I have written these solutions already on the board to save time. See, the first one, we have to convert kilometer to the millimeter. 1 kilometer is equal to 1000 meter by 1 kilometer. First kilometer has to be converted to meter, and then that meter into the millimeter, 1000 millimeter. So kilometer, meter cancel, and this 10 raised to plus 3 multiplied by 10 raised to plus 3 is 10 raised to plus 6. So we can say 1 kilometer is equal to 10 raised to 6 millimeter. The kilometer is to be converted into picometer. 1 kilometer is equal to 1000 meter divided by 1 kilometer, because 1 kilometer is nothing but 1000 meter. Kilometer we can cancel. The meter is to be converted to picometer. 1 picometer is equal to 10 raised to minus 12 meter. This meter we can cancel. This 10 raised to minus 12, in numerator it becomes 10 raised to plus 12. This 10 raised to plus 12 and this 10 raised to plus 3. 1000 is nothing but 10 raised to plus 3. 10 raised to plus 3 multiplied by 10 raised to plus 12 is nothing but 10 raised to 15. So 1 kilometer is equal to 10 raised to 15 picometer. Then milligram has to be converted into kilogram. 1 milligram multiplied by 1 milligram is nothing but 10 raised to minus 3 gram. And 1000 gram is equal to 1 kilogram. So this milligram we have cancelled. Gram we have cancelled. This 1000 is nothing but 10 raised to plus 3. In numerator it is 10 raised to minus 3, because 1 by 10 raised to plus 3 is nothing but 10 raised to minus 3. This 10 raised to minus 3 multiplied by 10 raised to minus 3 is 10 raised to minus 6. So 1 milligram is equal to 10 raised to minus 6 kilogram. Similarly, milligram has to be converted into nanogram. This milligram, 1 milligram is 10 raised to minus 3 gram. And this 10 raised to minus 9 gram equals to 1 nanogram, because nano stands for 10 raised to minus 9. Milligram, gram we have cancelled. This minus 9, and it is multiplied by 10 raised to minus 3, it becomes 10 raised to minus 3 multiplied by 10 raised to plus 9. And 10 raised to minus 3 multiplied by 10 raised to plus 9 is 10 raised to plus 6 nanogram. Then another one question we have already given. Speed is equal to distance traveled by time. So distance traveled is equal to speed into time, because they have asked for the distance traveled by the light in 2 nanoseconds. So speed is 3 into 10 raised to 8 multiplied by time is 2 nanoseconds. But that nanosecond, here it is, unit is meter per second. This unit is meter per second. This is meter per second, and this is in nanosecond. So I have to convert this nanoseconds to seconds by the same methods which we are using already. So multiplied by 1 nanosecond is equal to 10 raised to minus 9 second. Nanosecond get cancelled, and we get that time factor into seconds. 3 into 2 is 6. 10 raised to plus 8 into 10 raised to minus 9 is 10 raised to minus 1. This is meter per second for speed, and for time it is second. Second get cancelled. So the distance travelled will remain meter. So it is 0.6 meter equals to 6 into 10 raised to minus 1 meter. Then I have one more question. 5.96 gram per cubic centimeter density is to be converted into SI unit of density, kilogram per cubic meter. 5.96 gram per cubic centimeter into 1000 gram is equal to 1 kilogram. So we got gram into kilogram. This gram we can make cancel. but this cubic centimeter is to be converted into cubic meter. We know that conversion. 1000 cubic centimeter is equal to 1 cubic decimeter, multiplied by 1000 cubic decimeter is equal to 1 cubic meter. Cubic decimeter, cubic decimeter, cubic centimeter, cubic centimeter. We have cancelled. What remains is 5.96. This 1000 also we can cancel. This 1000 is nothing but 10 raised to plus 3 kilogram per cubic meter. So it is 5960 or 5.960 into 10 raised to plus 3 kilogram per cubic meter. So these are the 3 homework questions I have given. I hope that you got the correct answers. I have already told you, if you are not getting correct answers at this particular time, don't worry about it. They are very simple. Maybe you need my physical presence to make the things simple. That will happen in due course of time. So don't worry about it. Only you have to try again and again. If you have made any mistakes into it, you can correct those mistakes. You can pause this video and you can write these solutions. Right, so this is about the various units and their conversion. Now we'll go to the next part of our syllabus. So in physical quantity measurement, we have numerical coefficient and the unit. And till now we have learned about various units of various physical quantities and their interconversion. Now we have to concentrate on the numerical part, which we are reporting in the measurement. So we can say that we have to learn about the significant figures. Again, one of the very important aspect in the measurement of the physical quantity. Now when we measure any physical quantity, or when we deals with scientific measurement, there is uncertainty associated with every scientific measurement. So I will write here one sentence, that there is always uncertainty in every scientific measurement. Every scientific measurements. Of course, one scientific measurement is exception to it, which is counting. So there is uncertainty, means there is probability, possibility that our results are not 100% accurate. We'll see 2 reasons for uncertainty, but this uncertainty does not exist in the counting. For example, in this classroom, if there are some students are sitting here, and I have been asked to count those students, and I counted one by one, and if there happens to be 50 students, anybody can count that students and they will get the same result. It is not that I counted 50 students and some will count 49, or some will count 51, or some will count 49.5 or 50.5. There is no such possibility, because in counting, if we do not make mistake in counting, right, then there is no uncertainty into it. That's why when attendance is taken, everybody accepts that attendance, because there is no scope of uncertainty in that measurement. But when we do an experiment and report readings, there is possibility of uncertainty. Now there are two main causes of this uncertainty. One is the skill of observer. Skill of observer means who is doing that experiment, who is observing that phenomenon. Another is the limitations of apparatus which we are using. That also one of the main reason for uncertainty in the measurement. For example, if we have taken 25 milliliter one normal HCl, of course this one normal is a new word for you, but just I am giving this example. You can understand this example without understanding the meaning of one normal. And we are reacting it, versus means we are reacting it. One normal sodium hydroxide, and we want to know how many milliliter of sodium hydroxide is needed. We know that this is strong acid, this is strong base, and they neutralize one another. So the correct value would be, if this is 25 milliliter, this also should have been 25 milliliter, the correct value. But if there are 3 students and they are performing this experiment, one student will report 24.9 milliliter, another will report 25 milliliter, the third will report 25.1 milliliter. This happens in the practical, that we cannot get exact answer because these two limitations are there. Sometimes observer is not skillful enough to know the reading because it requires tremendous presence of mind. When you do the practical, you will observe that. Already you might have done some practical in your school level syllabus also. So we can say that this is the true value. This should be the correct answer. So only student B has got the correct answer. A and C, they are not getting the correct answer. Right. So this limitation A and C had because of they lack the skill of observing the reading, but B has observed correctly. Right. So this is one reason. Skill of observer may sometimes gives us wrong result. Now sometimes there is limitation of apparatus. For example, you are measuring the mass and you are measuring it by ordinary balance and you are measuring it by chemical balance. You may get this 1.20 gram, and for chemical balance you get 1.2045 gram. So this is supposed to be more accurate because after decimal point here only 2 places are there and here 4 places are there. So it is more accurate and it is more reliable. That's why when you want to measure the correct mass, for example, you have small gold piece, and if you want to know its mass, you never goes to a kirana shop, right? Because that will not give us accurate picture. You go into the jewelry shop and get it done, because that balance is more accurate. That's why it is more reliable, isn't it? So when a reading is 1.20 gram, there is possibility that the mass may be in between 1.19 gram to 1.21 gram. There is always uncertainty into it, even though 1.20 gram is reported. It may be in between 1.19 to 1.21. It is not that the chemical balance is not having uncertainty. It also has uncertainty, but less amount of uncertainty. If you get 1.2045 gram, it means the mass may be in between 1.2044 gram, this 5.44 gram, to 1.2046 gram. So it is in between that. This mass has been reported by that digital panel on that balance, but it may be in between these two. So every apparatus has certain uncertainty. The last digit we can say is uncertain here, which is 0 here, and in this case this is uncertain. So it may have accuracy up to 0.01 gram, because after decimal point 2 places, so I can put here 0 and 1 gram. And what is the accuracy here? 0.0001 gram, isn't it? There is difference in this digit. 1 1 2 2 0 0 4 4 is same. 5 6 4 6 or 5. So there is only chances of getting wrong into the last digit, which is uncertain. And here is 0.01 gram, like that. So in these measurements, we come across this type of uncertainties. They are the part of our measurement. Even though we want the results to be more accurate and more precise, but this is not the way in which the scientific measurements are reported. There is always a large digit which is doubtful, and before those large digits they are more reliable. So when result is reported, this result is reported, we call it as significant figures. And in these significant figures, there is 2 figures in this particular number which are certain, and last which is doubtful, we call it as doubtful. Why we call it as doubtful? Because it may be 1.20, can be 1.19, or it can be 1.21. So significant figures is nothing but the number of figures which are certain plus 1 doubtful figure. So you just make the notes of this, because then you will understand what is the definition of the significant figures. So we can define significant figures as the certain digits. I write the SCF now, because again and again when we use this word significant figures, I will not write all here. So significant, all words, so significant figures is equal to certain digits. Certain means which are not uncertain, which are fixed, which are accurate, plus certain digits plus 1 last doubtful digit. Why we are keeping this doubtful digit with the resulting is doubtful? Because it has to be kept. There is no other way. We can round it off. We can ignore this and make some changes into this certain digits that we'll see afterwards. But when results are reported, they are reported in such a way that few numbers are fixed, certain, reliable, accurate, reproducible, and other numbers after that they are the doubtful. So that is called as the significant figures. Now there are certain rules of these significant figures, how they are arranged and how they are used and how they are counted. So we'll see one by one those significant figures, and then we have to solve some questions also to understand this concept. Many more questions will solve so that everything should be clear to us. There should not be any doubt. So the first rule regarding is that all non-zero digits are significant. This is the first rule, in that all non-zero digits are significant. I will give few examples here only. Again I will give some examples, but I will write these numbers only. We can take any number, but I have written some number purposely so that we can correlate with this. Example, if we have 42.3 and 243.4 and 24.123, and if we have been asked how many significant figures are there, we should not consider the decimal here. Ignore this decimal when we report the significant figures. So it is 1, 2, 3. So you can say it has 3 significant figures because all non-zero digits these are. 1, 2, 3, 4. There is 4 significant figures this number has. 1, 2, 3, 4, 5. This number has 5 significant figures. Very simple. All non-zero digits are significant. This is the first rule regarding this. You just count the digits and you will have idea about it. The second rule is zeros between two non-zero digits are significant. So if we are getting zeros between two non-zero digits, they are significant. I will give you some example here. 5.03, 5.604 and 4.0004. Yes, 1, 2, 3. This zero becomes significant. Digits. These are two non-zero digits, and zeros are coming in between. They become significant. So 1, 2, 3. It has 3 significant figures. 1, 2, 3, 4. It has 4 significant figures. 1, 2, 3, 4, 5. It has 5 significant figures. So try to understand the first rules. The all non-zero digits are significant. Zeros between two non-zero digits are significant. Now third is zeros place the 2 left of non-zero digit. Zeros place 2 left of non-zero digit are never significant. We'll take the examples of it. Example is 0.543. 0.543, 0.025 or 0.045 and 0.006. We can take any number, that doesn't matter. Only there should be consistency in your example and this example. That's why I am giving that number. So how many significant figures this number has? Zeros placed to the left, this 0 is placed to the left. So the non-zero digit, 5 is non-zero digit. So they are not significant. So you can say 1, 2, 3. Only 3 significant figures are there. These zeros are not significant, so only 2 significant figures are there. And these zeros are not significant, so only 1 significant figure we have in this particular number. So read these rules once again. All non-zero digits are significant. Zeros between 2 non-zero digits are significant, and zeros which are placed to the left of non-zero digit are never significant. Now apart from that, there are 2 more rules. Yes, they are very important. See the 4th one. We are giving examples in the rules only so that it becomes more clear. The 4th one is that the zeros placed to right of decimal point. Yes, they are significant. Decimal point are significant. Right of decimal point. See here. The example 433.0, then 433.00 and 433.000. So this is decimal point here, and the 0 are placed to the right, so they are significant. And being these numbers are non-zero, they are significant. So number of significant figures here are 1, 2, 3, 4. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. Significant figures are there. So those zeros which are placed to the right of the decimal point are significant. See the next one. If number ends with zeros, very important rule, but these zeros are not to right of decimal point. Because if they are right to the decimal point, we already settled it. They are significant. But if they are not to the right of decimal point, zeros may or may not significant. The zeros may or may not be significant. For example, if we have number 11,400, this number may have 3, 4 or 5 significant figures. 3 means 114 only. 4 means 1140 or 5 means 11400. Now how to know whether it is significant or not? It has to be reported in scientific notation and then it will be clear. For example, if 1.14 into 10 raised to 1, 2, 3, 4, this is the number we have, then we can say it has only 3 significant figures. These only 1, 2, 3. Because this 10 powers we do not consider into the significant figures. If we have 1.140 into 10 raised to still 4, 1, 2, 3, 4 only, after 1 only. But now in this factorial part, pre-exponential part, we have 1, 2, 3, 4. 4 significant figures. Or if it is 1.1400 into 10 raised to 4, we have 1, 2, 3, 4, 5 significant figures. So if number ends with zeros, but these zeros are not to the right of the decimal point, then we have to consider these zeros that they may be significant or they may not be significant. So these 5 rules I have given. The sixth one also we can say exact number has infinite significant figures. Exact number has, for example, value of pi, value of g, gravitational constant. It has infinite significant number because we can write decimal point and we can go on adding the 0. So exact number are having infinite number of significant figures. And last one we can say non-significant figures in the reporting of our answer. Non-significant figures in the measurements are rounded off. We have to round it off, which is doubtful digit. That we have to round it off. How to round it off? Certain rules we have to follow, but here only we have mentioned that non-significant figures in the measurements are rounded off. So this 6 and 7, by taking example, we will understand. But these 5 rules are very important and they have been applied to count the significant figures in the number. All non-zero digits are significant. Zeros between two non-zero digits are significant. The zeros placed to left of non-zero digit are never significant. The zeros placed right to the decimal point are significant. Zeros placed to the, if number ends with zeros and they are placed to the right of decimal point, then they may or may not be significant. So these are few sentences, very important sentences. We can understand them only by solving some questions. But before solving the questions, we'll just see how these non-significant figures in the measurement are rounded off. So to understand that, we'll make one table here. We'll make one table here to understand how rounding off is to be done with these numbers. Read again and again these statements because they are useful in solving the questions. MCQs also can be asked in various entrance examination to identify the significant figures in a given number. So we'll make one table. If the digit to be dropped in one column, because large paragraph is written in textbook, we are making it short. Last digit if digit to be dropped is less than 5, then last digit left unchanged, no change into. We'll take example and then only will understand this. First we'll make table. If it is more than 5, then last digit increase by 1. If it is 3, we have to make it 4, like that. Increase by 1. And if it is 5, the digit drop next to be 5. and if last digit is even number, this is left unchanged, and if it is odd, then it is increased by 1. Now I will give an example, then only it is clear, otherwise it looks very difficult when you read this. Very important table, but always remember this table, various entries into it. We have number here. Again, I will take specific example. 5.6724, 8.6526, 2.3524, and 7.4511. And we want only 3 significant figures here, only 4 in this number, only 2 in this number, and only 2 in this number. See, I will explain. This is 1, 2, 3, 4, 5 digit, but we have to convert this into only 3 significant figures, 3 digit only. So we should keep this, keep this, keep this. Now I have to drop this and of course this also, but this doesn't matter. We have to see this digit which is to be dropped. Immediately after that digit which we are retaining, this we are keeping because we want only first 3 digits, and this we are dropping. The digit to be dropped is less than 5. Left unchanged means we have to write this as 5.67. We have to ignore this 2 here. We can leave it as it is because it is less than 5. See now, 4 digits we want. 1, 2, 3, 4. It is greater than 5 now because 6 is greater than 5, more than 5. So last digit is to be increased by 1. So we should write 8.65 instead of 2. We have to write 3. We have increased by 1 because digit which is to be dropped is more than 5. Only 2 we need. This 2 we need. This is to be dropped, and digit to be dropped is 5 now. So if digit to be dropped is 5, we have to see to the before number 3 here. The 3 is the odd number, and that's why we have to increase it by 1. So we write it as 2.4. 3 is increased by 1 because if 5 is to be dropped, the before that digit 3 is there, which is odd. Now only 2 we need here. This 1 and 2. This 5 to be dropped, but digits were retaining is even. So it is increased by, no need to increase by 1. If it is even, it is left unchanged. So it is 7.4. Try to understand this. They are not difficult examples. 5.67, 8.653, 2.4 and 7.4 should be our answer. The digit which is to be retained is given by question. How many significant figures we should have in this answer? Then we should keep those figures, and apart from those figures, the next figure is to be dropped. If it is to be dropped, there are 3 possibilities: less than 5, more than 5, or 5. Less than 5, leave it as it is, no change. More than 5, increase 1 to the previous digit. If it is 5, look at the before digit. If it is odd, increase 1. If it is even, keep it is as it is. So there is no change into it. So these are certain rules. Why they made certain rules? So that there should be uniformity in our reporting, otherwise it would be difficult to get the result same throughout the scientific community. So to have some uniformity, they have made this rule. Now this is some rules we have followed. Now I will give you two questions here, or I will give three questions so that our understanding will be more clear. So I will rub this part. Already you might have written and understood this part. See the first question. State number of significant figures in each of the following. The first one, 0.000648. The second one is 7.0005. The third one is 312.84. The fourth one, 474.0. 6.45 into 10 raised to 6. Next is just pi, constant, and then this 6,000. So you just pause this video, read the rule, and try to give the answers here. The first answer is 3, 1, 2, 3. These digits which are to the left of non-zero digit, they are insignificant. These zeros which are in between these two non-zero digits are significant. So 1, 2, 3, 4, 5. This 1, 2, 3, 4, 5 once again, because all non-zero digits are there. Then this 0 which is to the right decimal point is significant, so this 4. This we should ignore this exponential part. 1, 2, 3 is there, so it is 3. And if you look at the pi value, it is 3.1428.571, isn't it? You can increase to any number here. So we can say it has infinite number of significant figures. And this one, it may have 1, 2, 3 or 4. The zeros may be significant or they may not be significant. 1, 2, 3, 4. It may have 1, if 6 into 10 raised to plus 3. 2, 6.0 into 10 raised to plus 2. Plus 3. 1, 2, 3. Yes, plus 3. 3 means like this. 1, if it is 6.000 into 10 raised to, actually it is 4, isn't it? It is 6 into 10 raised to 1, 2, 3, one digit. 6.0 into 10 raised to, again the same, 1, 2, 3. 3, 6.00 into 10 raised to 3. 4, 6.000 into 10 raised to 6,000 into 10 raised to 0. Means it is nothing but 6,000, isn't it? Multiplied by 10 raised to 0 is nothing but 6000 only. So it will be 4 like the same digit work out. So this is the way in which these significant figures can be calculated. Now I give 2 questions as the homework. The next question is write the following in scientific notation and determine significant figures. The first one is 0.40 and then 736, 0.00360, 10500, 72, and then 980. So this is homework for you. One more question I want to give you for homework so that you can understand this in better way. Express the following numbers up to 3 significant figures. Round up, we have to round it up. Up to 3 significant figures. Let's see how you round up. 306.35 means we have to keep only 3 digits here. This is to be dropped out. Less than 5. No need to change here. The answer is 306. Correct. What else you do yourself on the questions? Next one is 0.00388816. Third is 1.78975 into 10 raised to plus 4. Next is 25400 and fifth is 2.65986 into 10 raised to plus. So these are some questions I have given you for the homework. These 2 questions. Read once again what we mean by scientific figures, various rules applicable, how to round it off, apply it, not at all difficult. I hope that as always you will solve these 2 questions correctly. In next class, once again I will solve you. You have to just verify. Don't wait for next class that I will solve on the board and then you will solve. Let it be wrong, but you try yourselves. Thank you for watching this video.